So today we're going to talk about how hydrogen peroxide is used in rocket propulsion. And I'm Kylie. Okay. So the decomposition of hydrogen peroxide is a disproportionation reaction, meaning that oxygen is both oxidized and reduced into water in the form of steam, oxygen gas, and heat. This is favorable, and you can increase the rate of decomposition with temperature, increasing the concentration of hydrogen peroxide, and incorporating a catalyst. So in rockets today, I don't know if any of you have been to space, but the common monopropellant they use is hydrazine, which decomposes into nitrogen and hydrogen gas and ammonia, and is highly exothermic. So you get a large amount of thrust there, but it's very toxic. So there's a push to use green propellant in the form of hydrogen peroxide, and although you sacrifice some of your propulsion performance, there are some pros, essentially being that it's non-toxic. And also, hydrogen peroxide has a very high density, and so you're able to reduce the amount of space that you devote to your oxidizer. And so when you're going to space, you want to consider the amount of space you're taking up with you. And it's also easily stored. It's not cryogenic. You can store it at room temperature, and it can be an oxidizer and a monopropellant, whereas hydrazine has to work in conjunction with another oxidizer and bipropellant hybrid systems. So the mechanism in the rocket, your hydrogen peroxide is fed into a high-pressure chamber that contains your catalyst, and that undergoes decomposition into steam and oxygen. One thing I wanted to point out is that the steam heats up to about 978 Kelvin, whereas the silver melting point is 1,234 Kelvin, meaning that the silver is still stable under the high temperature. And so in a monopropellant system, that gas is then released, and conservation of angular momentum thrusts your rocket forward, and then in a bipropellant system, you also have that thrust from releasing the steam, but also oxygen can be used to combust your organic fuel. So, laugh. I did some computational work on this. So for the density of states, just to show that when I incorporate the two, it's a summation of the two into the system, and then notice the D character of the metal in the partial charge density, and if I had the absorption.
Which system are you exploring? Which model are you exploring?
The catalyst and peroxide.
Okay. So just explain your model. Peroxide and what?
Silver.
Good.
Okay. Please no interruptions. So then the key thing for my project was looking at the heat treatment and the molecular dynamics. So the top row is the thermalization spectra for the silver independently, the peroxide independently, and then the entire system, just to see that the silver is stable, so your catalyst isn't going to change, and then most of this is due to the hydrogen peroxide and the dispersion of kinetic energy when you heat it. And so the molecular dynamics file, notice the marked increasing and decreasing of temperature, indicative of bond forming and breaking. When you heat it, you allow for changes in electronic structure. Electron wants to move. And here is my first feature film. It's also on YouTube, the YouTube, apparently. Yes. Okay, so you can see evolution of intermediate products, and then also oxygen. I don't know if you can catch it real quick. But questions? Thank you.
Okay, thank you.